Okay, so last time we were talking about line integrals, okay? New concept and weird concept. So let me just quickly tell you once again that a line integral looks like this, and you have a vector function here. You have a line element here, and to solve this, we require number one, value of f, number two, Ri and Rf, and DL is also there. And number three, path. Three things are required. Here, solve this. Very, very weird. Three things are required. Now, I also told you that the quantity called work in physics is the line integral of force, right? Ri to Rf. So in this case, F is equal to force. DL is the line element or the small displacement that we have already seen. R, Ri is the starting point, and Rf is the end point. Okay. Starting point of what? End point of what? Starting point of motion, end point of motion. So the particle moves from Ri to Rf, and I can work out the work done by the force or by the forces acting on the particle, uh, provided that I know the force, I know the initial and final points, and I know the path that the particle takes. Now we had seen that there are limits. Limits are starting point of motion and end point of motion. So if we have a particle which is going to move from this point to this point, we're going to take a path like this, right? Then this would be defined as the initial position vector. This would be defined as the final position. Please never confuse yourselves with normal integration के limits, because normal integration में after carrying out the integration you actually place the limits into the nahi. So Ri and Rf have got nothing to do with the path. No. Ri and Rf have got nothing to do with the path of the particle. That is a completely different, independent piece of information that we require, right? So I told you in the last class that if you give me F and if you give me Ri and Rf, I am still unable to solve the line integral. I am still unable to carry out the line integral, and that is because I require the path as well. Right? Three things are required. ठीक है ना? Please do not have any sort of presupposition or preconception कि नहीं ये तो वैसा होना चाहिए, ये तो वैसा ही होना चाहिए, ये पुराना इंटीग्रेशन जैसा होना चाहिए, ऐसा कुछ नहीं है. We are learning something brand new. This is based on mathematics which we have seen, but this is completely new mathematics. So in normal integration जब आप इंटीग्रेट कर लेते हो तो लिमिट्स की वैल्यू सब्स्टिट्यूट करते हो, जो एक्सप्रेशन आपको आंसर आया, लेकिन यहाँ पे ये RI और RF, they are not for substitution. You don't substitute it anywhere. Okay. Eventually you might substitute. I will show you how that ultimately happens. But अभी के लिए this is just starting point and the end point, final point. Okay, so I'm going to change the slide, and we are going to calculate the work done by Earth. So remember, there were 5 objects in the vicinity of a system that could create or that could generate the phenomena of force, earth, surface, string, spring, and external agent, right? So I will now tell you how to calculate the work done due to these 5 objects. Once we have calculated how to find out the work done, then I'll tell you about the work energy theorem, which is the main chunk of this chapter. And I'll tell you how to apply work energy theorem in various cases. And then finally, we will learn the concept of potential energy. Okay, and then finally, इसके बाद भी एक छोटा सा और portion रहेगा, that of power. Power is not very different from what you have already learned in class 11 or class 10. Slight improvement on the definitions you learned in class 10. So power will take a very small amount of time. Okay, so first let's calculate the work done by these 5 objects, 5 external, 5 objects in the surrounding. First, of course, is the Earth, right? So what do you need to find out the work done by the Earth? Well, you need the force applied by the Earth that you already know, it is mg. Then you need initial and final points, okay? And then you need the path taken by the particle to go from the initial point to the final point. Okay? So let me draw. So this is the initial point. This is the final point. And the path taken by the particle is something like this. And this is the path taken by the particle. We are looking at it from the side. So this is the path taken by the particle. Please notice that the initial and final points are arbitrary and the path is also arbitrary. ये तेरे को शौनक कहाँ से इलिप्स दिखाई दे रहा है मुझे तो नहीं समझ में आ रहा है, तो मतलब इलिप्स तो नहीं है ये, आर्बिट्ररी, ठीक है ना, मैंने अपने मन से एक ड्राइंग बना दिया. ओके, सो अबे अर्थ का ऑर्बिट कहाँ से आ गया बे? वर्क डन बाय अर्थ है ये, अर्थ में सरफेस के पास एक पार्टिकल को यहाँ से यहाँ ले गए. ये इनिशियल पॉइंट है और ये फाइनल पॉइंट. एक पार्टिकल को एक आदमी उसको ऐसे उठा के, आप अपना पेन ले जाओ ना हवा में इधर से उधर, तो एक पार्टिकल को, हाँ, सो लेट मी जस्ट क्लैरिफाई, अगर डाउट आ रहा है मन में, सो लेट मी क्लैरिफाई. What you do is you take your pen and you hold it at a particular height. आपका हाथ बिल्कुल ऊपर होना चाहिए और आपका पेन आपके हाथ में होना चाहिए. Now you have to bring the pen to your table following any weird path possible, right? So any weird path you take and then you keep the pen on the table. So when you keep the pen on the table, then the initial point was when you were holding the pen very high. Final point is when you have kept the pen on the table. Now I want to calculate the work done on the pen. Work is done on an object by the forces which are acting on the object. तो ये पेन के ऊपर कौन कौन से फोर्सेस एक्ट कर रहे थे? ये पेन के ऊपर एज इट मूव्स फ्रॉम द इनिशियल पॉइंट टू द फाइनल पॉइंट, उसके पहले पेन क्या कर रहा था, उसके ऊपर क्या फोर्सेस लगे थे, उससे हमें कोई मतलब नहीं. फाइनल पॉइंट के बाद उसके ऊपर क्या फोर्सेस लगने वाले हैं वो उससे मुझे कोई मतलब नहीं। इनिशियल पॉइंट और फाइनल पॉइंट के बीच में जब आपने पेन को हाई अप अपने अबव द हेड रखा और उसके बाद से आप जिगजैग मोशन में नीचे लेके आए और आपने इसको टेबल पे रखा, then two forces were acting on the pen. Yes, exactly, yes. So first is the gravitational force that was acting on the pen because of the earth, and the second is the force by the external agent, which is you. That was the force acting on the pen. So two agents are doing work on the pen. One is the earth and the other is you, the external person. I am not interested in the work done by you at the moment. I am only interested in the work done by gravity on the pen. Okay? So I draw the initial point of the pen, I draw the final point of the pen, and I draw the path which has been taken by the pen. Right? This path, of course, has been forced on the pen by you. But since we are not talking about the work done by you on the pen, therefore we will assume that as the pen moves from this initial position to this final position, we will assume, or we will only take, or we will only consider the gravitational force acting on the pen, right? Because we want to find the work done by the earth. So I now start the maths. Work done by the earth must be integral of F applied by the earth dot dl from some initial position to some final position. Okay? Now, how do we solve this line integral? What is the way to solve this line integral? Well, the first thing to do is to divide this line integral into infinitesimally small line elements. Right now, I'm not going to, of course, infinitesimally small तो नहीं बनाने वाला हूँ मैं, but I will divide it into ये रहा पहला, ये रहा दूसरा, ये रहा तीसरा, ये रहा चौथा, पांचवा, right? And you get the right. So I have divided the path into infinitesimally small line elements. Okay. Next, what I need to do is that I need to draw the force vector, the F vector, the vector function जिसके ऊपर हम line integral carry out कर रहे हैं. We need to draw that vector for every dl. थोड़ा painful होगा, but I will try to do it. mg, 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 mg. Please notice that all these arrows that I am drawing, yellow arrows, all have the same magnitude and the same direction. Okay, मेरे diagram से लगे ना लगे उससे कोई मतलब नहीं. All the yellow arrows have a magnitude of mg and they are all vertically downwards. Okay. The next step is to find the angle between the force vector and the displacement vector or the line element. Okay, so let's do that. Let this angle be theta 1, let this angle be theta 2, let this angle be theta 3, let this angle be theta n. Okay, right? अभी तक आ रहा है सबको समझ में? किसी को अभी तक प्रॉब्लम नहीं होनी चाहिए. So let me call this DL1, DL2, DL3, DLN. Okay. ये कर्व है किसका? इसका मतलब क्या हुआ हार्दिक? मतलब नहीं समझ में आया मुझे. इसका ओनर कौन है? या इसको किराए पे किसने दिया है, क्या पूछ रहा है? किसका ग्राफ? कनेक्शन गड़बड़ हो गया था क्या हार्दिक? मैंने बताया ना क्या है ये पाथ। पाथ बोला ना बे, आना मेरे सामने है। ओके, सो नेक्स्ट what is the next step? Work done by the earth must be equal to mg dl1 cosine theta 1 plus mg dl2 cosine theta 2 plus mg dl3 cosine theta 3. Now you must be wondering, ये भैया ये लिखा क्यों जा रहा है ये? Why are we writing this? Well, there is a logic behind me writing this. Can anybody see what that logic is? Can anybody see what that logic is? हाँ हाँ, डॉट प्रोडक्ट, हाँ हाँ हाँ, नहीं डॉट प्रोडक्ट का समेशन है, वो तो हमने किया ही। हाँ, can you tell me what टाइम कहाँ से आ गया खुशी बीच में, समय कहाँ से आ गया? Can you tell me what this thing is in brackets? ये क्या चीज है? ये ये क्या चीज है? ये क्या चीज है? वेरी गुड तरुण, यस समझ गया, चैपल समझ गया। नहीं एमजी नहीं है वो। हाँ यस 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 आर्यन गुड। सो dl1 cos थीटा 1 क्या चीज है? वेल ये है cos, ये है थीटा 1, तो dl1 कोसाइन थीटा 1 कहाँ आएगा? dl1 कोसाइन थीटा 1 कहाँ आएगा? तो व्हाट आई कैन डू इज आई कैन, सबसे पहले तो ये थीटा 1 मुझे दिखाई दे रहा है कि ऑब्ट्यूज एंगल, तो अगर ये ऑब्ट्यूज एंगल है इसका मतलब ये हुआ कि ये तो माइनस में आने वाला है, ठीक है ना? कोसाइन थीटा 1 की वैल्यू माइनस में आने वाली है। dl कोसाइन थीटा 1 क्या होगा ये नहीं समझ में आ रहा है। dl कोसाइन थीटा 1 क्या होएगा? हाँ, dl कोसाइन थीटा 1 क्या होएगा? Let me draw this. Let me draw this. So, if I have this right angled triangle, then this quantity should be dl1 cosine theta 1. mg के opposite, हाँ mg के opposite, right? ये dl2 cosine theta 2 कहाँ आएगा? ये dl2 cosine theta 2 कहाँ आएगा? ये थीटा 2 अभी भी ऑब्ट्यूज एंगल है, ये अक्यूट नहीं है, ये 90 डिग्री से बड़ा है। इसका मतलब कोसाइन थीटा 2 तो नेगेटिव आने वाला है, तो ये dl2 कोसाइन थीटा 2 भी यहाँ पे अगर मैं ऐसे सीधी लाइन बनाऊंगा तो टेढ़ी मेढ़ी हो गई, आई एम सॉरी अबाउट दैट। dl2 कोसाइन थीटा 2 जो आएगा वो यहाँ आएगा ऐसे। अब ये dl3 कोसाइन थीटा 3 कहाँ आएगा? dl3 कोसाइन थीटा 3 कहाँ आएगा? अब थीटा 3 अक्यूट हो गया है, लेस देन 90 डिग्री, तो ये dl3 कोसाइन थीटा 3 कहाँ आएगा? dl3 कोसाइन थीटा 3 अब आएगा ऐसे। हाँ, अब ये dl4 कोसाइन थीटा 4 कहाँ आएगा? वो आएगा यहाँ पे। dl5 कोसाइन थीटा 5 कहाँ आएगा? ऐसे। dl6 कोसाइन थीटा 6 कहाँ आएगा? ऐसे। dl7 कोसाइन थीटा 7, ओके। उसके बाद से dl8 कोसाइन थीटा 8, उसके बाद से dl9 कोसाइन थीटा 9, उसके बाद से dl10 कोसाइन थीटा 10। वो 11 ही है, तो कोई दिक्कत नहीं। ये आ रहा है सबको समझ में? आई होप नोबडी इज losing track of what I am doing. So what I have done is that I have first, if you want later on, I can draw a bigger diagram. In fact, I will draw a bigger diagram. पहले इसको मैं खत्म कर लूँ। तो what I have done is I have simply applied the definition of finding out the line integral. So I had knowledge of, somebody told me previously कि भाई वर्क डन बाय अर्थ निकालना है, तो मेरे को अर्थ की वजह से फोर्स का मैग्नीट्यूड और डायरेक्शन दोनों मालूम है। उसके बाद से दे सेड कि ये इनिशियल पॉइंट है, ये फाइनल पॉइंट है, ओके। एंड देन they said that look, you have to follow this path, okay? This path is to be followed from initial point to final point. So I have divided the path into line elements. Number one, I have drawn the force vector mg downwards for every line element. I have found angles between the line elements and the mg vector for all line elements. And then I have worked out the dot product of mg and the line element for every line element. After working out the dot product, I realize that this dl1 cos theta 1 quantity, I realize that this dl1 cos theta 1 quantity is nothing but the component of dl1 along mg. But since cosine theta 1 or theta 1 is an obtuse angle, dl1 cosine theta 1 will come out to be negative. That means its direction will be opposite to mg, and this is what I have drawn here. Okay, and then I have drawn dl2 cos theta 2, and then I have drawn dl3 cos theta 3, and then I have drawn dl4 cos theta 4, and then dl5 cos theta 5, and so on up till the end. And like one of you said, okay, all we have to do now is to take mg common. All I have to do is to take mg common. And when I take mg common, what am I left with? So work done by the earth is equal to mg मैंने कॉमन ले लिया, और ये ब्रैकेट में क्या बचेगा? ये जो मैंने ब्लैक एरोज बनाई हैं, मैंने थोड़ा केयरफुली बनाने की कोशिश करी, लेकिन मैं फिर से बनाना चाहता हूं. सो आई एम चेंजिंग द स्लाइड. सो दिस इज द वेरी नाइस, यस शौनक, फाइनली this is the initial point, this is the final point. Okay, I'm going to choose a separate path now. This is the path taken. The path is still arbitrary, please notice. So we have this as dl, this as dl, oops, this as dl, then this as dl, then this, then this, then this, then this. Okay, the mg vectors are again constant. Good. Okay. Now, where is dl1 cosine theta 1? dl2 cosine theta 2. Here. dl3 cosine theta 3. The thing to realize is that जहां पे red arrow end होता है ना, उसी horizontal level पे काला arrow भी end होता है. So in this case, this is dl cos theta. Okay. In this case, this is dl cos theta. In this case, this is dl cos theta. Okay. And in this case, this is dl cos theta. Okay. And then here we have this as dl cos theta. Here we have this as dl. Okay. Now, if I were to draw the black arrows together now, if I were to draw the black arrows together, what will I get? Let me just draw some horizontal lines. If I were to draw the black arrows together, what will I get? ये पहला black arrow है, ये दूसरा black arrow है, तीसरा black arrow है, चौथा है, ये पांचवा है, ये छठा है. Yes. No, it is not the displacement. No. No. Please don't confuse. Displacement would be this. ये है displacement. This is displacement. The length of the black arrow, when the black arrows combine, exactly. Yes. क्या है ये black arrow की summation? dl1 cosine theta 1, dl2 cosine theta 2. क्या है ये? What is this? It is the height. Okay. So we arrive at a wonderful, yes. We arrive at a wonderful expression, and it tells me that work done is equal to mg into dl cosine theta 1 plus dl cosine theta 2 plus dl cosine theta 3, and all of this combined is nothing but the height between initial and final points. This is absolutely fantastic, because whenever I am asked to calculate the work done by Earth, or whenever there is a requirement, of finding the work done by Earth, whenever, I never ever have to bother with line integrals again. Okay? So I taught you line integrals. Okay? I want you to learn line integrals. I want you to know line integrals, but there is no way that I am going to let you carry out in a question a line integral. Since work done is the line integral of force, okay, and we know that in mechanics that there are only 5 objects which can generate force. Therefore, we are going to figure out the work done by these 5 forces, so that we never have to calculate the line integral for such forces. है? क्या लिख रही है? एक मिनट रुको. Surface of Earth. हाँ. मतलब सरफेस ऑफ अर्थ के ऊपर अगर आपने अभी बालकनी से अपने पेन को गिरा दिया तो जब वो जमीन पे गिरेगा तो वर्क डन बाय अर्थ ऑन दैट पेन, work done by earth on that pen will be equal to mgh. ये क्या हो गया है? एक मिनट रुको, मैंने कोई गड़बड़ की। हाँ, जी कांस्टेंट है ना, वी आर नियर द सरफेस ऑफ द अर्थ। एक मिनट रुको, समथिंग हैज हैपेंड, इट हैज हैपेंड फॉर द फर्स्ट टाइम। अबे क्या है ये? ओ अरे oh, I don't know how to get rid of this. ये क्या खुल गया है यार? हाँ चलो गया गया। Oh, चलो हाँ। So work done by Earth is equal to mgh. Whenever we have to calculate the work done by Earth, we only need to know the initial and final position. What we don't need to know is the path taken, right? It's weird. मैंने पहले बताया कि path पे डिपेंड करता है लाइन इंटीग्रल की वैल्यू, but it turns out that it is not always dependent on path. Sometimes for some vector functions the value of the line integral is independent of the paths, right? These are very special line integrals and they have a name, and we'll discuss the name later on. So work done by the earth is plus minus mgh. Why minus? Can anybody guess? When will I use minus? When will I use minus? Very good part, yes. हाँ, मतलब उल्टा ऊपर जाएंगे तो माइनस हो जाएगा। G is now a constant. H is the vertical distance between initial and final points. Okay? Plus, when object comes down, minus when object goes up. Ah. Now, I know you have seen this before. Okay? I know you have seen this as the potential energy before, okay, mgh. But please, 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 for God's sake, do not confuse this with potential energy. पोटेंशियल एनर्जी बिल्कुल अलग कीड़ा है, वो हम बाद में देखेंगे। फिलहाल पहली चीज जो आपको इस चैप्टर में याद करनी है, ये टू बी रिमेम्बर्ड है। पहली चीज जो इस चैप्टर में याद करनी है वो ये है कि वर्क डन बाय द अर्थ इज इक्वल टू mgh plus minus mgh, where h is the vertical distance between the initial and final points. Needless to say that you cannot calculate the work done if you do not know the initial and final points. Very, very important. Initial and final points क्या हैं? न्यूटन्स लॉज ऑफ मोशन हम पार्टिकल के एक लोकेशन पे लगा देते थे। पार्टिकल यहाँ है, न्यूटन्स लॉ ऑफ मोशन लगा दो भैया, कोई दिक्कत नहीं। लेकिन जब हम वर्क डन की बात करेंगे तो पार्टिकल के ऊपर जो वर्क डन है that will only be defined if the path of the particle is defined, otherwise it is not defined. Okay, you can't say what is the work done by the earth on the pen, मैंने टेबल पे रखा हुआ है, you can't do that. What is the work done on the pen by the earth when the pen moves from this point to this point, then I can talk about work done by it. Okay, next please take a screenshot. रिमेंबर वर्क डन बाय द अर्थ में अब आपको कभी भी लाइन इंटीग्रल वर्कआउट नहीं करना है, ये हम कर चुके। इसका रिजल्ट जो आया बहुत ही सिंप्लीफाइड सिंपल सा आया, दैट्स इट। नेक्स्ट इज वर्क डन बाय नॉर्मल रिएक्शन। वर्क डन बाय नॉर्मल रिएक्शन। ठीक है, अब ये कैसे करेंगे भाई? So the reason why we are choosing work done, the reason why we are choosing work energy theorem, the reason why we are going in for this extra tool of analysis is that just like you, everybody in this world hates the idea of constraints. Constraints are basically mathematical objects which make our life hell, which complicate our lives, so we want to get rid of constraints. The concept of work energy was invented precisely for this purpose. So whatever force is capable of generating constraint, right? Fortunately for us, the work done by this constraint force becomes equal to zero. What is the work done by normal reaction? Work done by normal reaction is zero. However, there are cases where work may be done by normal reaction. The reason why work done by normal reaction is zero is very simple. Because normal reaction is perpendicular to the surface. Normal reaction is perpendicular to surface. अगर हमारे पास एक ऐसा ऑब्जेक्ट है, एक्सेप्शंस, अगर हमारे पास एक ऐसा ऑब्जेक्ट है M1 M2, normal reaction on M1 is like this and the normal reaction on M2 is like this. ठीक है ना? So in this case, work done by normal reaction on M2 is not equal to zero. Work done by normal reaction on M1 is not equal to zero. However, the sum of these two quantities, that means work done by normal reaction on M2 plus work done by normal reaction on M1 is equal to zero. Right? So it turns out that work done by normal reaction on a system of particles is always zero. So work done by अब उसके उसके डिटेल में नहीं जाएंगे. वर्क डन बाय नॉर्मल रिएक्शन ऑन ए सिस्टम इज इक्वल टू. लेकिन अगर आपसे कोई पूछेगा कि वर्क डन बाय नॉर्मल रिएक्शन ऑन M2 कितना है, वो जीरो नहीं. ऑन M1 कितना है, वो जीरो नहीं. लेकिन दोनों का एडिशन जीरो, इक्वलेंट. दोनों का जो वैल्यू आएगा, एक प्लस आएगा, एक माइनस आएगा. दूसरा, अगर मेरे पास एक लिफ्ट है और ये लिफ्ट ऊपर जा रही है और इस लिफ्ट के अंदर एक बॉक्स है, इसके ऊपर लिफ्ट के सरफेस ने नॉर्मल रिएक्शन लगाया. वर्क डन बाय नॉर्मल रिएक्शन ऑन M1 is not equal to zero. Work done by normal reaction on M1 plus work done by normal reaction on lift is zero. लेकिन work done by normal reaction on M1 is not zero, क्योंकि M1 के ऊपर नॉर्मल रिएक्शन वर्टिकली अपवर्ड लगा है और इसका एक्सेलरेशन भी वर्टिकली अपवर्ड है. तो नॉर्मल रिएक्शन और जो लाइन एलिमेंट हम बनाएंगे उनके बीच का एंगल 90 डिग्री नहीं होएगा. Having said all this, I have never ever seen a question where work done by normal reaction is not zero. Yeah? I have never ever seen a question where work done by normal reaction is not zero. ये जो एक्सेप्शन मैंने लिखा है, ये हो सकता है आपके सामने आ जाए, मैंने आज तक नहीं देखा. So I have not seen, I am yet to come across a question where work done by normal reaction is not equal to zero. 99.9999% of the questions, normal reaction will be zero. Okay, in some special scenario like this lift wala scenario, if somebody is crazy enough to ask you कि नहीं अब आप बताओ नॉर्मल रिएक्शन का वर्क डन कितना होगा, तो आपको नॉर्मल रिएक्शन इनटू कोसाइन थीटा इनटू पाथ लेंथ करना पड़ेगा to find out the work done by normal reaction. Okay, या फिर लाइन इंटीग्रल निकालना पड़ेगा, I don't. But as far as I have seen, work done by normal reaction is not equal to, is always equal to zero. Okay. Next, please take a screenshot and go to the next screen or write it down. I think you should write this down. Please write this down. Work done by earth, please write that down. Work done by normal reaction, please write that down. हाँ, पाथ मिलेगा ना. अगर आपसे वर्क डन बाय नॉर्मल रिएक्शन पूछ रहे हैं, आपको पाथ मिलेगा, बिल्कुल वो देंगे. यस. After you've written it down, please write a yes. Please type a yes so that I'll move forward. Okay. Next is work done by friction. कोई भी केस होगा, वर्क डन बाय नॉर्मल रिएक्शन जीरो होगा. एक्सेप्शन मैंने बता दिया है. अगर आप वो एक्सेप्शन को चेक करोगे तो यू विल कीप ऑन लुकिंग थ्रू क्वेश्चंस. तो क्वेश्चन मिलेगा नहीं, बहुत रेयर. नहीं, मैं बता रहा हूँ, मैंने आज तक तो नहीं देखा. नेक्स्ट इज वर्क डन बाय फ्रिक्शन. इसमें मैं आपकी कोई हेल्प नहीं कर सकता हूँ. And work done by friction you will have to find out using the line integral. However, there is a shortcut, and this shortcut is applicable only for a very small subset of questions which satisfy certain criteria. So I will tell you that shortcut, and we will figure it out. What is the shortcut? So this is a fixed inclined plane of angle theta. I take an object of mass m and I move the object to the top of the incline. कोई तो मैंने force लगाया. So this is me pulling the object. So what are the forces acting on this object? mg, normal reaction, friction. Friction will be mu n. Friction will be mu n because of the fact that it is moving. I'm telling you it is moving. I take it up to the top. That means that I am telling you this is the initial point, this is the final point. Okay. So let's calculate the line integral of friction. First, we divide the path into elements. Here are element. Actually, I could have done it in one arrow, but ठीक है, तीन मैंने बना दिया. Next, I have to draw the forces, and since I'm only finding out the work done by friction, I'm not bothered about what is the work done by me. I'm not bothered about what is the work done by gravity. I'm only bothered about the work done by friction. Right? So for all these line elements, I will draw only the friction force. So here the friction force is like this, mu n. Here the friction force is like this, mu n. Here the friction force is like this, mu n. So I have divided the path into line elements, and for every line element, I have drawn the force. Next, I need to find out the angle between the line element and the force for every line element. So here it is 180 degrees, right? Here it is 180 degrees, and here also it is 180 degrees. Obviously, मैं उसको ऊपर ले जा रहा हूँ, फ्रिक्शन जो है डाउन द इंक्लाइन है. Obviously, every step I take, the friction will always be opposite to the displacement of the object. So now I can write this thing, work done by friction is equal to mu n dl1 cosine theta 1 plus mu n dl2 cosine theta 2 plus mu n dl3 cosine theta 3. But what is so special here? Cosine theta I can take common because the angle between the force vector and the displacement vector always remains constant, right? So I can take this theta common and I will be left with a standard integral. In fact, this is even better because this mu n is constant. I can take this out as well. So I'm left with mu n cosine theta integral of dl. And what was integral of dl, remember? Integral of dl was the path length. So this will be equal to mu n cosine of 180 degrees into length of the path. Right? And what is n here? How much is n? Well, this is mg cosine theta. और इस डायरेक्शन में तो कोई मोशन हो नहीं रहा है, इस डायरेक्शन में तो इक्विलिब्रियम होना चाहिए। तो मेरे पास आ जाएगा माइनस म्यू एम जी एल कॉस थीटा। राइट, नाउ व्हाट इज एल कॉस थीटा? What is L cos theta? What is L cos theta? Base of the triangle. Yes, yes. Or is very good. Yes, Shivan. Yes, yes, yes. It is the horizontal distance between the initial and final points. So work done by friction is equal to, I will again write plus minus depending on friction opposite है या towards है, mu mg into the horizontal distance between initial and final points. Right? But this definition of work done, please don't close your eyes and apply. This definition of work done will only be invoked when the particle is traveling along a straight line. Okay, particle is traveling along a straight line. Okay, and the value of n is equal to mg cos theta. Even if the particle is traveling along a curve, तब भी apply हो जाएगा, provided that the value of n is always mg cos theta. अगर n की वैल्यू mg cos theta है तब आप ये चीज अप्लाई कर सकते हो, नहीं तो नहीं. Please write this down. Write this and then I'll give you one question to solve. फिर आगे बढ़ते हैं. लेंथ ऑफ कौन से कर्व में कहाँ करवाया? कौन से कर्व में? हाँ, यस. हाँ, इंटीग्रल डीएल हम उसमें कुछ नहीं देंगे, हम उसमें भी हॉरिजॉन्टल, ये फॉर्मूला एप्लीकेबल हो गया ना, हॉरिजॉन्टल डिस्टेंस बिटवीन इनिशियल एंड फाइनल पॉइंट्स लेंगे. हॉरिजॉन्टल डिस्टेंस बिटवीन इनिशियल एंड फाइनल पॉइंट्स लेंगे. आगे बढ़ो. कैन आई मूव? आगे बढ़े। अच्छा वो चेंज हो गया क्या? अच्छा। Friction, work done by friction. नहीं भाई, जीरो आंसर नहीं है। हाँ ये सही है। अच्छा, हाँ पार्थ, इसमें एल एल भूल गया। हाँ हाँ चल। हाँ यस, प्लस नहीं होएगा, प्लस तभी होएगा जब फ्रिक्शन और मोशन का डायरेक्शन सेम रहेगा ना। फर्स्ट स्टेप पाथ, मेरा कि दोनों येलो लाइन एक दूसरे के ऊपर रहनी चाहिए, बट फॉर विजुअलाइजेशन पर्पसेस मैंने अलग बना दिया। डिवाइड इनटू डीएल, 3 एरो ऊपर 3 एरो नीचे। ड्रॉ द फोर्स वेक्टर। जब ये ऊपर जा रहा है तो फ्रिक्शन पीछे रहेगा, लेकिन जब ये नीचे आ रहा है तो फ्रिक्शन ऊपर हो जाएगा, और फ्रिक्शन की वैल्यू हमेशा म्यू एन रहेगी। एंगल बिटवीन फोर्स एंड displacement is always 180 degrees. Therefore, work done by friction, which is equal to integral f dot dl, will be equal to f dl1 cosine theta 1 will be equal to cosine theta integral f dl will be equal to cosine theta f एक constant है. So this will be equal to cos 180 into mu into n, which is mg cos theta, into 2l, right? Because the path length is 2l. So work done by friction in this case minus 2 mu mg l cos theta. Right? तो आंख बंद करके अंधाधुंध ये काम नहीं करना है कि ऊपर गया फिर नीचे आया तो वर्क डन बाय फ्रिक्शन 0. अगर वर्क डन 0 आ रहा है इसका मतलब, at least in the language of physics, is that you don't require to input any energy, or whatever energy you input you will get it out, right? As far as friction is concerned, it is a dissipative force, and therefore you can never find a situation where friction is acting, motion हो रहा है और net force 0 आ जाएगी. Never ever will that be there. Friction is also a force for which the path is very important. तो जिन लोगों ने आंसर खट से पहले दिमाग में 0 आया, बिल्कुल, I'm not blaming you. Your mind is, thinking perfectly. You thought that since the particle has come back to its original position, therefore work done should be 0 because the displacement is 0. लेकिन यहाँ पे आपका जो 10th वाला फॉर्मूला है वो नहीं काम करेगा, क्योंकि 10th वाला फॉर्मूला मैंने बताया था कब काम करता है. मैंने बोला था आपको कि ये तभी काम करेगा, फोर्स इंटू डिस्प्लेसमेंट इंटू कॉस थीटा, जब नंबर 1 फोर्स और डिस्प्लेसमेंट का एंगल हमेशा कांस्टेंट रहेगा, जो कि यहाँ रहता है. नंबर 2, जब फोर्स का मैग्नीट्यूड कांस्टेंट रहेगा, जो कि यहाँ रहता है. एंड नंबर 3, कि वो अगर बिल्कुल ही स्ट्रेट लाइन में चल रहा है तब 10th वाला फॉर्मूला काम करेगा. लेकिन यहाँ पे ये स्ट्रेट लाइन में नहीं चला, क्योंकि ये गया और फिर वापस आया. 2 अलग अलग स्ट्रेट लाइन है. Therefore, your 10th वाला फॉर्मूला fails miserably. और जहां पे लास्ट क्लास में आपने 10th वाला फॉर्मूला लिखा था, उसके जस्ट ऊपर जो फॉर्मूला लिखा था वो था कि अगर फोर्स और डिस्प्लेसमेंट के बीच का एंगल हमेशा सेम रहता है और फोर्स का मैग्नीट्यूड हमेशा कांस्टेंट रहता है, then the work done is given by force into cosine of angle multiplied by path length. वो यहाँ पे काम करेगा. Okay. Next, work done by tension. So before I actually tell you what is the work done by tension, I want you to work it out yourself. Now this may seem contradictory, but believe me, it is going to be very, very fruitful for us. So we have a standard Atwood machine, 2 kilo 3 किलो. Find work done by tension on 2 kg and 3 kg block if they are released from rest and move for 2 seconds. जो भी आपने अभी पिछले 2 एग्जाम्पल्स में 3 एग्जाम्पल्स में जैसे आपने मेरे को देखा वर्क डन कैलकुलेट करते हुए, ठीक वैसे ही यहाँ पे वर्क डन कैलकुलेट करना है बाय टेंशन ऑन द 2 kg ब्लॉक इफ दे आर रिलीज फ्रॉम रेस्ट एंड मूव फॉर 2 seconds. नाउ इफ यू रिमेम्बर ए लॉन्ग टाइम बैक मैंने आपको बोला था कि एटवुड मशीन का एक्सेलरेशन और टेंशन याद रखना, और मैंने बोला था मैं 2 महीने बाद 3 महीने बाद पूछूंगा, और ये वो टाइम आ गया. You can of course figure it out, but if you remember then it will be very very fast. Yes, good. Yes, that is the acceleration. चलो इसको करो जल्दी से. Figure this out. Figure out the initial position, final position, path. Divide the path into line elements individually for the 2 kg and the 3 kg block. Figure out the value of force. Figure out the angle between the force and the line element. हे भाई लिखा हुआ है क्वेश्चन में, यार पढ़ना. ये कुछ गड़बड़ लग रहा है हार्दिक तेरे आंसर में. ओके, फिर 3 वाला निकालो. क्या मालूम, सबका अलग अलग आंसर आ रहा है. दोनों का निकालना है शायद, एक आंसर नहीं चाहिए। हाँ, okay. So what is going to happen is that the 2 kg block is going to go up, and the 3 kg block is going to go down. So the path of the 3 kg block is this. Path of the 2 kg block is this. The tension, sorry, the tension on the 3 kg block will always be upwards, and on the 2 kg block will also be upwards. So the angle between tension and the line element will be 180 degrees for the 3 kg block, 0 degrees for the 2 kg block. Now the value of tension for a standard Atwood machine is given by 2 m1 m2 g upon m1 plus m2, which will be equal to 2 into 3 into 2 into 10 divided by 5. This goes away, and therefore the tension will be 8 into 3, that is 24 meters. The acceleration of an Atwood machine is given by m1 minus m2 upon m1 plus m2 into g, which will be equal to 3 minus 2 into 10 upon 5, which is equal to 2 meter per second square. Since the acceleration is constant, therefore the displacement in 2 seconds will be half into a into t square, which is equal to 4 meters. Therefore, this distance is 4 meters. This distance is 4 meters. Okay, now I can figure out the work done. So the work done on the 2 kg block will be equal to tension का value into the displacement का value into cosine 0. Work done on the 3 kg block will be equal to tension का value to displacement का value into cosine of 180 degrees. Please notice that I have directly used the formulas. Okay, I've directly used the formulas because number one, the forces were constant. Number two, the path was a straight line. And number three, most important, which should have been number one, the angle between the force and the line element always remains the same. So this is equal to plus 96 joules. This is equal to minus 96 joules. Therefore, work done by tension on the system, right? Whenever I say system, I mean, in this case, I mean I'm choosing more than two objects as a system. Work done by tension on the system is how much? Work done by total work done by the tension on a system is how much? Total work done is the work done on individual components added up. Is and this is exactly what I wanted to show you. This is exactly what I wanted to show you. Work done by tension is equal to zero. Remember, tension is a force which generates constraints. And like I said, the whole concept of work energy is that we don't want constraints. Okay? Work done by tension is zero. However, just like normal reaction, there are exceptions. And the exception is that if you are asked to find the work done by tension on one object in a system, then it may be possible that work done by tension may not be zero, as it is here. But if you are asked to find out, which in all cases it is going to be that way, work done by tension on a system where they have two blocks or four or five or three connected to each other by strings, then work done by these strings, work done by the tension in these strings will always be zero. Okay. Again, 99.99999% of the questions, work done by tension will be zero. Reason why I gave you this question, because this question as it is was asked in one of the ITJ advanced exams, right? तो अगर मैं आपको बता दूं वर्क डन बाय टेंशन जीरो है तो ऑब्वियसली आप आंसर जीरो लिख के आ जाओगे. But work done by tension zero होता है normally because tension is perpendicular always to displacement. But अगर tension perpendicular नहीं है displacement के, then work done by tension will be there. However, work done by tension on a system again goes to zero. Not on the individual object, but on a system it is zero. आया समझ में सबको? वर्क डन बाय टेंशन कहीं भी आएगा उसको जीरो लेके चलना है. ओके, आगे बढ़ते हैं. वर्क डन बाय ए स्प्रिंग, ये क्या होएगा भाई? So since work done is defined as integral f dot dl, okay? But if there is only one dimension, okay, that means that जो भी फोर्स लगेगी, जो भी डिस्प्लेसमेंट होएगा, वो एक ही डायमेंशन में हो सकता है. Okay? If that is the case, then ये डॉट प्रोडक्ट का तो मतलब ही नहीं है, क्योंकि अगर हम एक ही डायमेंशन में हैं तो वर्क डन अगर सपोजिंग एक्स एक्सिस के अलावा है, then work done must simply be equal to f dx, right? So in one dimension the dot product simply becomes f dx. Okay? So we know that for a spring F is equal to minus kx. So work done is equal to xi to xf minus kx dx, which will be equal to minus half kx square from xi to xf Therefore, work done will be half kxf square plus half kxi square, which is equal to half kxi square plus, sorry, xi square minus xf square. Again, this is to be remembered. Okay, xi square minus xf square. Where xi is the initial elongation or compression of spring. Xf obviously is the final elongation or compression of the spring. This is the work done by spring. Please remember that it is half k xi square minus xf square. Okay? Please write this. हो गया, लिख लिया. Okay. Now, before I talk about the work which is done by external agents, before we go into that, I must first introduce the concept of the work energy theorem. So, work energy theorem. So, the work energy theorem says that the summation of work done is equal to the change in kinetic energy of the system. I can give you a very crude proof of this. F is equal to ma. This means that F is equal to m into v dv by dx. Okay. एक minute. So F dx is equal to mv dv. And if I integrate both sides, left hand side I get work done. और यहाँ पे I will get half mvf square minus half mvi square, which is defined as kinetic energy. So kinetic energy is equal to half mv square. हाँ प्रतीक्षा क्या पूछ रही है? अच्छा, does energy's definition remain the same? एनर्जी की क्या डेफिनेशन थी मुझे याद ही नहीं है। क्या था? Capacity to do work, right? हाँ, that remains the same. Work and energy are same. You do work, you get. It's क्या बोलेंगे? It is work which generates kinetic energy. You do work, you get kinetic energy. For the moment, we are only talking about kinetic energy. After some time, we'll talk about potential energy, right? And then I will show you, you will actually see, I will not show you, that various forms of energy that you have studied are actually only kinetic energy or potential energy. There is no other form of energy, right? Except photon वाला energy हम बोल सकते हैं कि हाँ वो energy है. So kinetic energy and potential energy. जब waves आ जाएंगे, then you can have one more type of energy. But in mechanics, there is only kinetic energy and potential energy. Okay, so sum of work done is equal to change in kinetic energy. And the method of application is actually very, very simple. Number one, choose the initial and final points. So if you have one particle, तो कोई problem नहीं है. If you have more than one particles, then you have to choose the initial and final configuration, right? For example, we chose the initial and final configuration here. So this represents the initial configuration of the system, and this represents the final configuration of the system. Right? So if you have only one particle, उसका initial position क्या है, final position क्या है, काम खत्म हो गया. If you have a set of particles, तो उनका initial configuration क्या है, final configuration. Basically configuration मतलब है कि initial position of all the particles आपको मालूम होना चाहिए और final position of all the particles आपको मालूम होना चाहिए. Second, find all forces that act on the particle or the system that act on the particle or the system as it. हाँ बोल ना भाई, बोल.
सर अगर F इक्वल टू ma है तो सर अगर हम m को कांस्टेंट रख रहे हैं तो a बदल रहा है, तो a के साथ f भी बदल रहा है, तो सर इंटीग्रल f dx में f को कॉमन क्यों लिया फिर?
मैंने कहाँ कॉमन लिया? मैंने बोला कि ये चीज वर्क डन. मैंने इंटीग्रेशन सॉल्व कहाँ किया?
फिर तो मतलब अगर f को कॉमन लेके फिर इंटीग्रल dx करेंगे तभी तो fx आएगा ना.
नहीं क्यों भैया, क्यों एफ को कॉमन क्यों लेंगे?
सर वर्क डन f इनटू डिस्प्लेसमेंट होता है तो f कॉमन है तब.
मैंने अरे तो फिर वही फिर कूद गया तू 11th 10th में. वर्क फोर्स इनटू डिस्प्लेसमेंट होता है, कुछ और होता है. वर्क क्या
fs
होता
cos
है?
थीटा. हाँ सर,
डर लगता है कहीं तो
इंटीग्रल ऑफ एफ डी एक्स।
हाँ, ऐसे बोलना। अब उसमें
हाँ
एफ
जी सर।
कॉमन ले सकते हैं नहीं ले सकते हैं, ये तो बाद में पता चलेगा ना। अभी तो हम चुपचाप उसको इंटीग्रल एफ डी एक्स बोले, और ये वन डायमेंशन में है। नहीं तो फोर्स उसका लाइन इंटीग्रल होता है वर्क डन, लाइन इंटीग्रल ऑफ फोर्स इज वर्क डन।
यस सर। ओके
ठीक
सर,
है।
थैंक्स। यस सर।
So second step is to find all forces that act on the particle or the system as it transitions from the initial configuration or initial position to the final configuration or final position. Okay? And then what you do is summation of work done by all forces is equal to final kinetic energy minus initial kinetic. Okay, please write this. Oh yeah, can I move? स्प्रिंग क्या क्या बोल रहा है शिविर, नहीं समझ में आया मेरे को। एक मिनट। हाँ बोल।
सर वो जो के एफ और के आई है वो हम क्या, मतलब अगर स्प्रिंग के लिए मैं ये चीज लिखूं,
स्प्रिंग के लिए नहीं, स्प्रिंग के लिए नहीं करेंगे ना। स्प्रिंग किसी ब्लॉक से कनेक्टेड होएगा ना। वर्क एनर्जी थ्योरम तो आप किसी ब्लॉक पे लगाओगे ना, किसी पार्टिकल पे लगाओगे। अगर
अच्छा
स्प्रिंग
अच्छा ठीक है
उसके
समझ
ऊपर
गया।
फोर्स लगा रहा होगा तो स्प्रिंग उसके ऊपर उतना वर्क करेगा, जो एक्सप्रेशन अपन ने लिखा हुआ।
ओके।
क्योंकि शिवेन ने स्प्रिंग की बात कर ही दी है। हाँ, समेशन लेना, यस। सारे वर्क डन निकालने हैं, इंडिविजुअल अब नहीं निकालना, सारे वर्क डन निकाल के ऐड करना है। हाँ भाई, चलो करो ये। Follow the 3 steps: initial configuration, final configuration, work done due to all the forces. It is. Yes. So first we need to talk about the initial and final configuration. नहीं शोना गलत. If I leave the block from here, then the block is going to go down, down, and at a certain point, it will be the spring will be at its maximum elongation. Right? Now, this word you are going to hear a lot of times, so it is better that you get familiar with it. मैक्सिमम इलोंगेशन का मतलब क्या हुआ? मैक्सिमम इलोंगेशन का मतलब हुआ कि अब उससे ज्यादा इलोंगेशन नहीं होने जा रहा. अगर उससे ज्यादा इलोंगेशन नहीं होने जा रहा है तो यहाँ पे इस ऑब्जेक्ट का वेलोसिटी क्या होना चाहिए? अगर इससे ज्यादा स्प्रिंग इलोंगेट अब नहीं करेगा तो यहाँ पे ऑब्जेक्ट का वेलोसिटी होना चाहिए 0. ओके. और ब्लॉक इज रिलीज्ड दिया हुआ है व्हेन द स्प्रिंग इज एट इट्स नेचुरल लेंथ दिया हुआ है. इसका मतलब यहाँ पे भी वेलोसिटी 0 थी, इनिशियल से फाइनल ये ऑब्जेक्ट आया, राइट. सो आई हैव फिगर्ड आउट द इनिशियल एंड फाइनल कॉन्फ़िगरेशंस ऑफ द सिस्टम. Now I need to figure out what is the work done on the system, right? नहीं गलत. What is the work done on the system? Who is doing the work? Well, Earth is doing the work. Definitely, Earth is doing the work because it is coming down. And the spring is connected to the block, so spring is doing work on the block, right? So let's write the work done by Earth. Let's say that this comes down a distance of L. So the work done by the Earth must be equal to plus mgl. Plus mgl. Okay, and the work done by the spring must be equal to half k xi. मतलब कि इनिशियली कितना इलोंगेटेड था या कंप्रेस था इसका स्क्वायर, तो इनिशियली तो नेचुरल लेंथ पे है, इसका मतलब इनिशियली उसका इलोंगेशन 0 है, माइनस एक्स एफ स्क्वायर, मतलब कि फाइनल इलोंगेशन क्या है स्प्रिंग. अब अगर ये स्प्रिंग की नेचुरल लेंथ है, ऑब्वियसली अगर ये स्प्रिंग यहाँ तक आ गया तो ये जो चीज हो जाएगी ये स्प्रिंग की इलोंगेशन हो जाएगी, राइट. सो आई गेट हियर एल स्क्वायर. Initial kinetic energy we know is 0 because the object was released initially. Final kinetic energy we know is 0 because this is the point where maximum elongation has occurred. Okay, so we get mgl minus half mg, sorry, minus half kl square is equal to 0. This implies that L is equal to 2mg by 2. So this must be the maximum elongation. हाँ, ये बहुत अच्छा क्वेश्चन. Why can't we say that finally mg equal to kl, l is equal to mg by k? खत्म हो गई कहानी. हाँ, बता रहा हूँ. लास्ट पार्ट कौन सा? लास्ट पार्ट कौन सा? दोनों क्वेश्चन का आंसर दूंगा, पहले दूसरा क्वेश्चन में समझ लो कौन सा बोल रही है तुलिका, कौन सा लास्ट पार्ट. अच्छा, ये तो सिंपल यहाँ से निकाला ना, ये तो एल और एल कैंसिल हो गया, फिर एल की वैल्यू निकाल दिया यहाँ से. So what happens why can't I apply mg is equal to kl and get L is equal to mg by k? See, when I release the object, okay, when I release the object, then what is happening? When I release the object is under the influence of gravity. Because the spring is at the spring is not applying any force on the object. So you remember the hierarchy of things I told you. पहले force लगता है, force की वजह से acceleration होता है, acceleration की वजह से velocity change होती है और velocity की वजह से position change होती है. So here, as I release the system, gravity is acting on the block, but the spring, because it is in its natural state, is applying no force. Because of gravity, then there is acceleration, and because of this acceleration, the block develops a downward velocity, and because of this velocity, the block moves down. The block has a displacement downwards. But the moment the block moves down, the spring gets elongated. Okay, now we are talking about the motion of the block by a few millimeters, by a few nanometers. So the elongation of the spring is very, very small. However, it is there. Therefore, there is a force kx acting upwards now. But this kx force is very small as compared to mg. Therefore, the net force is still downwards. Therefore, the net acceleration is downwards. And therefore, the net velocity downwards will increase with time. अब टाइम थोड़ा और आगे बढ़ा तो जो वेलोसिटी है पार्टिकल की वो डाउनवर्ड डायरेक्शन में थोड़ी और बढ़ गई, तो नीचे की तरफ उसका जो डिस्प्लेसमेंट है वो थोड़ा और बढ़ गया. अब kx भी थोड़ा और बढ़ गया, लेकिन ये kx अभी भी mg से कम है. तो जो नेट फोर्स एक्ट कर रही है ब्लॉक पे वो अभी भी डाउनवर्ड. इसका मतलब एक्सेलरेशन डाउनवर्ड है. इसका मतलब वेलोसिटी डाउनवर्ड डायरेक्शन में इंक्रीज करेगी. तो वेलोसिटी और इंक्रीज कर गई, डिस्प्लेसमेंट और रैपिडली नीचे हो गया, kx और बढ़ गया, लेकिन अभी भी ये kx mg से कम. kx साइजेबल हो गया है, लेकिन अभी भी mg से कम है. तो नेट फोर्स अभी भी नीचे, नेट फोर्स अभी भी नीचे, छोटा ही सही, स्मॉल, because kx is rapidly growing. So net force is still downwards, therefore the acceleration is still downwards, and therefore the velocity downwards will still increase, but at a smaller rate. So because of the fact that the velocity is increasing downwards, at some point, velocity keeps on increasing, at some point mg becomes equal to kx. And when mg becomes equal to kx, the net force on the block becomes zero. But the velocity of the object is still downwards. So it will cross that equilibrium point. It will cross that mg is equal to kl point with a great velocity, with a large velocity. But when it crosses it, now kx becomes greater than mg, slightly greater than mg. So the net acceleration now, net force now is upwards. So the net acceleration is upwards, and the downward velocity now starts to decrease. लेकिन वेलोसिटी डाउनवर्ड है, इसलिए डिस्प्लेसमेंट अभी भी डाउनवर्ड ही होएगा. और जब डिस्प्लेसमेंट डाउनवर्ड होएगा तो kx और इंक्रीज करेगा. जब kx और इंक्रीज करेगा तो kx माइनस mg फोर्स इंक्रीज करेगी, अपवर्ड फोर्स इंक्रीज करेगी, अपवर्ड एक्सेलरेशन इंक्रीज करेगा, लेकिन वेलोसिटी तो डाउन है, वो वेलोसिटी कम होएगी. बट सिंस द डायरेक्शन ऑफ वेलोसिटी इज डाउन, डिस्प्लेसमेंट विल बी डाउन. और ऐसा होते होते करते 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 the velocity ultimately of the object will become zero. But now kx is far greater than mg. In fact, we can work out kitna kx. So net force is upwards now. अब ये object ऊपर की तरफ accelerate करेगा, and the cycle will continue, right? And therefore it will execute oscillatory motion. Okay? भी आया समझ में कि क्यों नहीं होएगा? mg is equal to kx क्यों नहीं लिख देंगे हम? ओके, अच्छा ठीक है, बाकी अगली क्लास में करते हैं भाई. ये 2 घंटा बोल बोल के मैं पागल हो गया. चलो, we'll start with work energy theorem in the next class. अच्छा हाँ, मैं भूल गया ना, वो दिनेश सर अभी थोड़ा, हाँ मैं अभी अभी बोलता हूँ मैं दिनेश सर. चलो guys, I'll see you tomorrow I think, right? हाँ हाँ, Zeal Academy ये रहा. चलो भाई, बाय 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 बाय.